And it's my great pleasure to present talk by Professor Hoang the Tuan. And you can see the title of his talk. Thank you for agreeing to deliver a lecture at our seminar. And please go ahead.
Thank you, Professor Alexey and Vladislav, for giving me a chance to present my work to everyone. My talk title, separation of solution and the attractivity of fractional order positive linear system with variable coefficients. Okay, fractional differential equation is a topic of research that has received a lot of attention. Their latest application can be found in the review paper and recently published monograph. As success from ordinary differential equation when studying the stability of fractional order differential equation, one often uses the following to approach the linear relation stability methods and the Lyapunov candidate function methods. Unfortunately, however, both of the approach mentioned above don't seem to be applicable to systems with many fractional order derivatives. Okay. Up to now, there are two strategies commonly employed to study the asymptotic behavior of solution to fractional system with multi-fractional derivatives. First, take the Laplace transform to obtain a characteristic polynomial, then rely on different techniques such as Liquid's theorems, Mikhailov stability criterions, Roche theorems, and Cauchy argument to investigate the position of the roots of this polynomial, depending on the situation where zeros are unstable or unstable regions. It's the conclusion that the solution of the system converges to the origins or to infinity. The second name is use the principle of comparison. This method is especially useful for class of system where the order generation is fast-paced reserved. Fortunately, fractional order positive system have this property. We review some contribution for the directions. It's paper by Sen and Nam. They have explored stability criteria for multi-order fractional positive linear system with bounded linear. After that, Tuan Hoang and Nam have provided an extended version for the stability of such system where linear is unbounded. By combining the candidate Lyapunov function and comparison argument, Bichicha and Swarov's Ganegos have shown the global attractivity of system under the influence of multiple time varying linears. Zia et al. Have studied the global stabilization in incommensurate order memristor-based network with time varying linears. Based on developing new comparison techniques, that are compatible with fractional order derivative and denies. Tuan and Thick have really obtained the attractivity of couples positive linear system. Less multi-index alpha has we consider the system. The question of what is the solution of a fractional differential equation can intersect were discussed by Ditham and Ford. The main difficulty of the problem for those class is his dependence of their solution. Kong and Tuan have rigorous proofs that solution starting as the difference point of scalar fractional differential equation don't intersect. However, in the multi-dimensional case, it's very surprising that they have shown that solution derives from different initial condition of scalar of fractional order system can intersect motivated by the work of Kong and Tuan and inspired by this theories published in the paper by Tuan and Thick. We want to prove separation of solution and lower estimates of solution to the system. One, then by comparative argument, we search for difference criteria to characterize the global attractivity of multi-order fractional positive linear system with variable coefficients and bounded denies. We introduce some notation. Some notation from the positive system. Now is equal the definition of Riemann-Liouville fractional integral and capital fractional derivatives. For more detail, the capital fractional derivative, we introduce the book by Ditham and the paper by Vladislav. Consider the system 1. The system is equivalent to the integral system, the system 3. The system 1 is said to be positive if for the input non-negative omega, the output phi omega is also non-negative. For the system 1 is positive if the matrix A is Messner and the matrix B is non-negative. Now we introduce some useful auxiliary results. We recall some result on the scalar fractional difference equation. Consider the equation 4, which assumes the function f is continuous and satisfy the Lipschitz continuous on the second variable. Our first contribution is the following theorems. If the function f satisfies the Lipschitz continuous the Lipschitz condition, then for any two different initial values, the solution corresponding don't miss on the interval z. Now we give some bounds for solution to a scalar equation. For two solutions, x1, x2, we have the estimate about the lower estimate. In the case, the origin is a trivial solution to the equation 4. We obtain the lower estimate for the solution x. It is not difficult to obtain the lower estimate for the solution. Okay. With some bound of solution to the equation 4. Now we can establish the non-local dynamical system. We define the evolution mapping. A two-parameter family of mapping VST is called a two-parameter flow. If VST is continuous as a function of three variables, and the mapping VST is a homomorphic, and this family satisfies the following flow property. Okay. The second contribution to the result. The following statement holds for the scalar equation. The evolution mapping generated by the equation 4 is a rejection. The equation 4 generates a two-parameter family of rejection by its evolution mapping. The family VST generated by the equation 4 is a two-parameter flow. If f is linear in the space variable x, then the two-parameter flow generated by the equation 4 is a flow of linear operator. Based on this result, we give the definition of the non-local dynamical system generated by the equation 4. We give some distinguished feature of the two-parameter flow generated by the fractional differential equation. However, it is very surprising for a higher dimension system. the situation is different. We have the result for any dimension d greater than 2. There exists a system with a property that it has two different solutions, x1, x2, with the initial condition, which intersect each other at some finite time. Hence, the high dimension system of fractional difference equation does not generate a dynamical system. Okay. Do you have any question?
Usually we have questions in the end.
Okay.
So please proceed.
Okay. Yeah. Now we discussed on the separation of solution to multi-order fractional positive linear system with variable coefficient and bounded delays. Our first contribution in this section is the result below. Consider the system 1. Suppose that A is Meissner, B is non-negative. For the initial condition omega and C satisfy the condition. Then two solutions, phi omega and phi C of the system don't miss on the interval. Okay, if we evolve some addition condition on the initial condition omega C, we show that two solutions, phi C and phi omega, is strict separate. Strictly separate. If the matrix A satisfies the condition, then for any initial condition omega and phi satisfy, we observe to the solution is strictly separate. Now we give some lower estimate for solution. With the estimates, we can build the local dynamical system for the system. Which equals the result is a paper by Differential and Tuan. Yeah. Okay. Based on the positivity of the system, sorry. Sorry. Now we introduce a generalized version of the theorem 4 by Differential and Tuan for mixed order system. Based on the result, we can build the local dynamical system for the system 1. quite the same. Quite the same for the scalar scale. For the scalar case. Okay. Now we talk about the global attractivity of fractional order positive linear linear system. Consider the system line. The positive system is said to be globally attractive if for any initial condition omega we have the limit these are plays a key role in the rest of the talk. Consider the system. Suppose that the matrix A is magnitude, B is non-negative, F decay to the origins. Then if the matrix A plus B is the solution P converges to the origins. Now we talk about the attractivity for the system fractional order with the order are different. Consider the system line. Assume that the matrix A is magnitude, B is non-negative, A is bounded by the matrix A has, B is bounded the matrix B has. If A has plus B has is Hooke's matrix, then every non-trivial solution of the system converges to the origins. Moreover, the solution phi omega with any the initial condition omega is dominated by continuous non-negative function phi star satisfy. Okay. In the case when the system lies is not uniformly bounded by a system with constant coefficient that is globally attractive, but is only essentially dominated by a system with this property based on a level comparison techniques proposed by Tuan and Thick. We also obtain a criteria for attractiveness of this system. However, due to the complexity of the research subject, the rest of confidence of the solution to the equilibrium of the system is this an open problem. Now, consider the system line. Assume that the matrix A is magnitude, B is non-negative. Outside the main diagonal of the matrix A and B, the entries A easy, B easy satisfy the estimate. On the main diagonal of the matrix, we have the condition K2. If the matrix 18 plus 18 is Hooke's, then the system is adjective. Okay. Now we consider the system with order equal. In this case, we can give accurately the rest of conference of their solution to the equilibrium. Okay, consider the system. In this case, the fractional order are equals. Suppose that the matrix A is Meissner, B is non-negative, A is bounded, A has, B is bounded, B has, and A has plus B has E Hupfist. Then there exists positive constant C and eta such that the solution phi satisfies the estimates. In this case, the rest of conference of solution to the origins is the subpolynomial by the Mittag-Leffler function. Okay. Finally, is by the idea that emerges when proving the stability of linear differential equation using the Harmonic inequality. We obtain the result on global attractivity of system when the rest of conference of its solution to the origin when requirement for dominance uniformly or asymptotically of the coefficient in theorem 20 and 23 are not justified. Okay. Consider the system 12. Assume that matrix A is Meissner, B is non-negative. Moreover, suppose that there exists gamma and the non-negative vector W satisfy the estimates. Then for X initial condition omega, we can find a constant F such that the estimates holds. Okay. Now we present some specific example. Okay. Consider the system 16. It is obvious to see that A is bounded by A has, B is bounded by B has, A has is Meissner, B has is non-negative, A has plus B has is Hupfist. Then the condition in theorem 22 verifies. Hence, the system 16 is global adjective. Now we depict the opposite of the solution to the system 16 with the initial condition omega. Okay. Now we consider the system 16. In this case, the A bounded A has B bounded B has. However, in this case, the matrix A has plus B has is not a Hurwitz matrix. So example 2 is not within the scope of the theorem 22 because we choose 18 between. In this case, 18 is Messner, 18 plus between is Hurwitz. Then by theorem 23, we conclude the system 16 is global adjectives. We depict opposite of the solution to the system 17, subject the initial condition omega. Finally, we consider the example. Okay. In this case, we see hence the theorem 22. We cannot use theorem 22 to describe the asymptotic behavior of solution to the system 16. Moreover, theorems 23 also seem inappropriate to apply to this example. However, by choosing the vector W equals, then the inequality 16 in theorem 25 become with the help of theorem 25, it implies that the system 16 is global activity. Now we depict opposite of the solution of the system 16 with initial condition. Okay, thank you for the attention. Our talk is based on the following paper. Okay. Now we show some difference. Okay.
Okay, well, thank you very much for a very nice presentation. And we have time for questions.
Okay, yeah.
Yeah, Professor Muravnik, please go ahead.
Thank you. Let us open, for example, slide 31.
31, yeah. Okay.
I don't. Yes. Yeah. The system or the equation is the same throughout the whole lecture. You just number it by different figures. So the function q of x is non-negative because otherwise it won't be a delay. But the question is, suppose we assign it identically equal to 0, and equation 9 stops to be a functional differential equation, it becomes a fractional order differential equation. And the question is, for this problem with q equal to 0, Properties of solutions are classical. For example, it can be found in the monograph of Kilbas, Samko, and Marichev. Do your results remain to be valid in this case?
Sorry, I don't understand the question.
Just assign Q of X to be identical 0 and check whether your results remain to be valid.
I guess the Formula 9 function Q is 0. Yes?
Oh.
Yes, sure.
Oh.
Just to check whether the results coincide with classical one in this simplest example. It's not only the simplest, it is a degenerative example. So there is no guarantee that they will coincide, but this is the reason for this interest. Well, maybe this is not a question for a couple of minutes. Perhaps you can treat this as a kind of advice. Maybe it is interesting to look in this direction.
Okay. You can see the. Okay. Okay. The system lies is quite the same as the system 1. Is the equivalent is a integral system 3 with the initial condition.
Yes, but we have a function Q of U in system 3 as well. The question is what happens if Q is equal to the identical 0.
Oh, for the case Q equals 0.
Yes, and the equation becomes differential equation.
Yes.
Differential one.
Yes. If the Q equals 0, hence it's the equation without the delay.
Well, I guess it's a question more than for future verification,
right? Can you
I agree. Yeah.
Okay, can you send me the question in via email or type can you
okay, I shall contact the organizers and they will redirect my email to you.
Yes.
If I don't load you too much, Alexey.
Okay, no problem.
Yeah.
But maybe more questions. Maybe I'll have one short question. Here in the equation, in the top of this page, you have you consider real case, right? So your functions are real functions, right?
Sorry?
So values of your functions are real numbers. These are real functions, right?
Yeah.
So you don't consider kind of complex situation, maybe complex parameter alpha. Can alpha be complex parameter, for instance?
Oh, is this paper we consider the case alpha equal to 0 to 1.
Yeah.
Okay. For the case alpha equal 1 is the equation becomes ordinary differential equation.
Yes, I understand. But the question was, can alpha be a complex parameter, a complex number with real part between 0 and 1?
Oh, yeah. Oh, sorry. Yeah. You use the multi-case, the multi-index alpha has. Yeah.
Okay, this may be also a question for kind of discussion after the talk. Well,
Yeah.
maybe more questions. Well, if not, no. If no more questions, then we'll thank our speaker for a very nice presentation again.
Okay.
Thank you for providing us with a lecture,
Okay.
and thanks to everyone who came to this seminar. And we'll see you in 2 weeks.